Okay, now we are going to obtain the second part of the solution. We already have bx and by. So with by I have already obtained this, and as you remember, I obtained this term with b infinity nu x. So after the simplification comes is kind of easy because this b infinity goes here, and I didn't tell you, b that, and in that way. But the 1x go here, what x, so we have here that. So in that way we have this term that is similar to this other term, but here we have also b infinity who goes here, b infinity squared, but because of this breaks like this. So we have the same term, nu b infinity divided by x, that is that we have here, and then we have the other function b infinity divided by nu x. This is eta, in fact. So we have here eta multiplied by, here is the second derivative, fb prima eta minus eta de eta. And here we have also 1/2, and the 1/2 is on the both terms. So then we have this already that I have already write to you. Let's now do the second part. Now we will obtain, because we have already bx equal to u infinity by f de eta, like here, f prima. That's right, f prima. So, okay, so now we can put the second derivative, where the first derivative of x with respect to x is simple. This one is b infinity. We derive again this one, and we have f, the second derivative, and then we have the eta and the x, the eta and the x. So we are going to obtain that derivative. That is easy, well, not so easy. I will write what is here. Eta is equal g by nu by u infinity divided by nu by x. Nu is the viscosity, x is the coordinate in the x-axis, and divided by, elevated to 1/2. So it's simple. We have here y divided by 2 because of this 1/2, and we have here, because this is minus, is on the quotients, we will have a sinus minus here. So if I'm right, yes, that's right, we will put here this sign minus. So okay, and here we have, here would be 1/2, it would be x to the 3.5, but elevated to that power. But because we can put like this, it's the same, x, 1x a la 1/2, 1/2 by 1x is the same result like this. Okay? Yeah? Okay, they're a little tricky. So we have here already that's simple, and we would have, well, that's right. That's the result. So we would simplify like this, partial bx by x equal minus u infinity divided by 2, then multiply by f b prima de eta, and by this term, u infinity by nu x, okay, a la 1/2. Okay, that's right. So now we can obtain the other derivative, that is partial bx divided by partial by. I will also delay this one already. Okay, then we have the other derivative, because this is the second part, it's only algebra, and we have here b infinity by f b prima de eta, that's the same, but here we have df by dy, d eta by dy. And d eta by dy, because we have here the function, is very simple, so we have here bf by only the constant term in y. Here is y, here is the constant term. We have only y u infinity by nu x elevated to 1/2. So it's a simple term also, so we don't have so much difficult, well, simple in some way compared to maybe other equations that are more complicated in nature. So that's the second part. So we have already 4 of our derivatives and terms that we need. And the only term that we are missing is the second derivative of u with x. And I will put like this here. I will not deduce, you can do because you already have it would be here the partial bx by x, and we have here it would be just deriving bx because we already have bx, partial bx with x, that is minus u infinity divided by 2x, and then here is eta and second derivative. Well, you do this derivative inside here and you see what it goes. This is for your homework. If I would leave you homework in a classroom, but this would be, I would put only the result is u infinity by the term that is already in many cases, nu x elevated to 1/2, and that would be with the third derivative of f with x cubica, and here it's not to 1/2, it's only like that. Okay, this is the last term that we were needing. And so after all this algebra and all these partial differential equations and partial derivatives and all that, we only have to, what did Blasius, he put it, all the terms is here in her boundary layer equation plus b partial b u with y equal nu, that's our, so he put all the terms here and make the algebra and make substitutions, and with some little complication he obtained this equation that is called Blasius equation, could be, and this is Blasius, I would say, not Blasius. So this is the third derivative of f, derivative with respect to eta, plus f multiplied by the second derivative of f by the eta squared, and that would be equal to 0. So after a partial differential equation that I have already put here, u partial ux plus b, that is the boundary layer equation, we have come to a simple, more simpler maybe, differential equation. This is of third grade, but it's only one variable, so that's the advantage of doing this method. This equation, you already have to solve it. It's not solved yet. You just only isolate and all that. No, you have to solve it. You can use numerical methods. You can use a series solution, and that's what Blasius used, a series solution. And he obtained that. He finally obtained his solution, and in that way he can calculate some quantities. I have another video where I show how with the tabulated solution of f in function of eta, we have different values of eta, 0.1, 0.5, 0.9, 1, 2, 3, so, and we have the values of f. In that way we can obtain, for example, the stress on the boundary layer, how is the force that is making the plate to displace. We can have the thickness and several quantities. So, well, more the thickness, the boundary layer, the stress. I think there are the members, and well, velocities u and v in function of x and y. So, I will put only the name of the article because I would like to show you that this guy, he became famous for this article. He was German, so I will put it in German. It sounds a little bit funny, but not funny, complicated. And so the name is H. Blasius. I will put, the name is very long, so I will put over here. Here is Gren, Schick 10. If someone of you is of German origin, maybe. Ian, I'm Mexican, I'm very Mexican, very Aztec, I would say. Plus, I came with a t-shirt of France today, but this is not, I'm Mexican, and I speak Spanish, of course. Lexictane, and meat, kleine, is a flus, it hasn't come to fly or win, maybe flus, you can maybe flux haben, and meat, kleine, if you know German, because I don't know German, Lebung. Okay, that's the name of the article, and it was in a Zeta Math and Physics, something like that, journal in German. And the year it was 1908. So it's a little bit more recent than the relativity theory of Einstein in 1905. So maybe it's the same kind of year. You know, some of the discoveries come together. So he was the guy who made this. The solution is only a laminar flow solution. So if you want to obtain a turbulence, which is more with the real, you have vortices here, and the vortices kind of diminish more and reduce more the energy. It's a little bit different, but in some way you can use a similar approach maybe with the von Karman solution. Von Karman is more simple, but it gives solution very near. And I maybe will explain the von Karman and also about some things about turbulence in another class that I would can have you in internet. So well, if you want to donate or something, I will open an account. Maybe if you want to just donate $50, $1 just for seeing this class and maybe enjoying some other things, well, you are welcome. But if not, it's no problem. You can already see the class also. So thank you very much and have fun and take care and good week. And we have to come to December. So well, this is me. If you didn't know me, hello. So goodbye, my friends.